So we're pivoting into a new conversation related to analyzing data. And in the past, when we've talked about analyzing data, it's largely been in a qualitative context where we're looking at, piles of information, so that's sort of words and text. And now we're going to be looking at piles of information that are more numbers or categories and arranged in sort of data sets. And so thinking about some statistical techniques, but also thinking about how to present that information in a way that's informative, how to avoid some common mistakes in terms of data management that pop up. And so a variety of things related to data analysis. So one of the things that we oftentimes want to know or be able to communicate about a variable piece of information is sort of what is the central tendency? What's sort of normal? What's the average kind of situation? And so we use average in sort of a colloquial sort of everyday kind of sense, but there's actually sort of three statistical ways of thinking about sort of what's normal or what's the average. So there's the sort of technical, like what is actually the average, what we call the mean in statistics, which is calculated the way you learn to calculate an average, right? You add up all your cases, the values for all those cases, you divide by the number of cases, and you have your average or you have your mean. We also have the median, which is where you line your cases up and the values in your cases up from smallest to largest, and you find the sort of middle value in that, and that gives you a sense of sort of where the middle is. This works pretty well with continuous variables, sometimes called interval ratio variables. It also works with ordinal variables to kind of find the middle category. You can do that. And then we have the mode, which is the most common category. And if you're working with categorical variables and data, this is probably the most useful statistic that you have for talking about central tendency. It's just what's the category that has the most cases in it? What's the largest category? I obviously wouldn't recommend using this for a continuous or interval ratio variable. Something like age, knowing what's the most common age isn't necessarily a useful thing to have and to be able to communicate to people. A second thing that we're interested in trying to communicate to people is sort of how spread out is our data around that central tendency, around that sort of average, that middle point. And so there's a couple different ways that we can communicate this, right? So we can think about the range, which is the difference between the maximum value and the minimum value. And so that sort of gives you a sense of, okay, if my average is 100 and my range is 0 to 10,000, maybe that helps me kind of visualize mentally sort of what that range looks like. We can also think about that in a more technical sense with variance and standard deviation. And these are just sort of two different ways of sort of thinking about the same statistical process. They just communicate a little bit differently. So with variance, what we're doing is we are taking each case and looking at the value and comparing that value to the mean and then subtracting the difference. And sometimes the value is going to be higher, sometimes the value is going to be lower. So we square that value to get rid of the negative signs, basically, because a positive times a positive is a positive, and a positive times a negative, or I guess, and a negative times a negative is a positive. So then the values are always going to be positive. We can add them together, sort of build up a sense of squared differences. And then we can divide that by the number of cases in our data set. And so it sort of gives us the average amount that we're missing the mean value, but it's the average value that we're missing the mean value squared. So it doesn't necessarily communicate particularly well when we're thinking about variance, but we can sort of fix that a little bit and take the square root of that, and that gives us the standard deviation. And the standard deviation is just the average amount that our cases are off from the mean value. And that communicates fairly well. And people will oftentimes cite the standard deviation as the most common way of communicating how spread out your data is. Another thing that we do when we think about a variable is, so how is it distributed? So we can think about the mean, we can think about the standard deviation, but things aren't always sort of symmetric. They aren't always sort of neat and tidy. And so one way to kind of get a sense of how data is distributed is to use a histogram. There's other kind of techniques as well. People will use, raindrop or thundercloud kind of graphs, or they'll use violin plots, or they'll use box and whisker plots. But I tend to find histograms to be a really useful way of thinking about data. And so if you think about what a histogram is doing, it's taking the range of all the values across the x-axis. So in this case, it goes from basically 0 to 4, and then it kind of groups those into sort of little ranges. and it counts how many cases are in the ranges. And so the higher the bar, the more cases are falling sort of in that narrow range. And you can kind of get a sense of how things are distributed. Earlier, when we were talking about sampling distributions, we sort of used this sort of curve, this normal distribution sort of curve. In reality, data doesn't distribute that way. It doesn't distribute as a perfect curve. But when we're thinking about histograms, we can kind of make that jump. We can kind of say, well, this thing kind of has a curve. It kind of goes up and then it kind of goes down and tails off. And I can kind of see that in this pattern in this histogram. And so it's oftentimes the case that we use histograms to talk about the distribution of our data and to kind of get a sense of visually what it's doing. And this can help us spot sort of really odd things. So if you have a case that's like extremely high, so I gave that example of, 100 is your average, 0 is your minimum, and 10,000 is your maximum, right? On this, you're going to really get a sense of that. You're going to pick that up pretty quickly that, wow, something is really, really odd about that 10,000 case. I should also flag that for a long time, Excel didn't have the ability to easily produce histograms. It does now, which is kind of a handy trick. The other thing that I would say is that we can maybe start talking about these distributions with some additional language. We can talk about whether it's symmetric or whether it's maybe skewed one direction or the other. We can talk about whether it's bimodal, which doesn't necessarily mean like a single category that's the largest. We can sort of see like there's the one sort of area on the side that's kind of larger. Sometimes we have bimodal distributions where there's sort of like two humps in our data. Maybe that's useful to kind of think about or to be able to describe. There are some statistics that can help us to describe our distributions a little bit better. So some people will break their data down into what are called entiles, but nobody uses entiles. Quartiles or deciles. Entiles just means that whatever number of categories you want to break it into. Percentiles are commonly used in communicating sort of standardized test information, that kind of thing. But the basic idea is you line your data up in order from smallest to largest, and you slice into as many categories as you need. And then you can maybe talk about those differences between the first quartile versus the second quartile versus the third quartile. And maybe that kind of helps to visualize what is happening with that data and how it's distributed. Some people will report the skew of the data. So again, when we're talking about these histograms, in this case, we've sort of got the main sort of center of the data, and then it sort of trails off to the side a little bit. We can maybe say that that data is skewed to the right. It has a tail that maybe is a little bit longer to the right. And so that in that case, we would say that there is positive skew, that the skew is moving off to the right in the positive direction. If the tail is moving off in the left, it's moving in the negative direction. We'd say that there's a little bit of a negative skew on that data. And so that's something that we can measure statistically, or we can just communicate sort of verbally. And kurtosis is a third way of sort of statistically measuring distributions. I'm not going to try to describe the math behind it, but the basic idea is that we oftentimes end up with normally distributed data, or that's a common pattern that we can reference. We can say, well, our data is kind of normally distributed, but it might not be perfectly normally distributed. That refers to a very specific mathematical equation. Sometimes our distributions look normal, but they're actually kind of thin in the center. There's not a lot of cases in the center, and there's more cases on sort of the tails than we would see with a true normal distribution. And so in that case, we would say that there is positive kurtosis. It's thin in the center, kind of pointy, and the tails are kind of thick. There's more cases out there. We could have negative kurtosis where the center is kind of thick. It's all kind of clustered in around that sort of middle, and there's not a lot of information in the tails. Maybe that's useful. I have never found that a particularly intuitive statistic to use or to communicate, but it is used widely enough that I think it's worth having in the back of your mind that, oh yeah, there's this thing called kurtosis, and it has something to do with normal distributions.